So what we're going to look at now is how I can use the Doppler effect to detect planets moving around distant stars. So the Doppler effect actually affects the spectra of the planet. So talking about this, we'll have Dr. John T. Horner. This video was made by him while he was working as an astrophysicist here at the School of Physics at the University of New South Wales.
We can use the spectrum of a star to work out what's in the tenuous outer atmosphere, and from that we can infer what a star's made of. We can actually use these absorption lines in a star's spectra to go one step further, and we can use them to learn about how that star's moving through space. And to do that, we're going to use techniques that you first came across when talking about how a speed camera works back in topic 7. We're going to have a brief reminder of the Doppler effect. Now, the most day-to-day application of the Doppler effect is something you hear when you're walking, maybe to university, walking around the city centre. If you hear the siren on an ambulance or a police car, when that vehicle is moving towards you, the siren is high-pitched. You have Nino, Nino, Nino. When the vehicle passes you and moves away, the frequency of that sound drops and is lower pitched, and the pulsing is slightly slower, so you get Nino, Nino, Nino. That's the Doppler effect. And the same is true of light as is true of sound. When a light-emitting source is moving towards you, the distance between successive crests of the light wave is squashed together slightly, because in between emitting one crest and the next crest, the source has moved towards you slightly. What that means is that when a light source is moving towards you, the wavelength is shifted slightly to the blue, or the light is blue shifted. Similarly, when the source of light is moving away from you, in the time between it emitting one peak and the next peak of the light wave, it's moved slightly further away, and so the wavelength you observe is slightly longer than the wavelength that would be emitted if the source was stationary, and so the light is redshifted. Because the absorption lines in the star are created at very, very specific wavelengths, they're created at the wavelengths moving with the star, and so if the star is moving away from you, the location of those dark lines in the spectrum will be moved very slightly to the red. If the star is moving towards you, the location of those lines will be moved very slightly to the blue. The faster the motion, if the star is moving more quickly towards or away from you, the greater the shift will be. And so this gives us a tool by which we can measure the velocity of the star along our line of sight, the velocity of the star towards the Earth and the velocity of the star away from the Earth. That's illustrated here in this figure, which shows you at the top panel an example of an unshifted spectrum. You've got light running from the blue to the red, and laid on top of that light are the dark absorption lines. The second figure shows the case when those spectral lines are slightly redshifted. You still see all of the light from blue through to red because the star is emitting at all wavelengths and at all frequencies. So the red light that has been redshifted out to beyond wavelengths the eye can see has been replaced by blue light that has been shifted in at the blue end. So everything's just moved along, but you still see blue through to red light. But the location of the lines laid across the spectrum have moved slightly to the red. That light's redshifted because the source is moving away from us. On the bottom panel, you see the opposite situation where the source is moving towards the Earth, and in that case those spectral lines are moved slightly towards the blue. What this means is that so long as we can get a good measurement of the spectrum of a star, and we have some way to calibrate it, say by looking at the wavelengths that those lines would be at in the lab, then we can compare the two and calculate what velocity the star is moving with along our line of sight. And that's exactly like the trick that we talked about when we spoke about the speed camera back in topic 7. So we now have a tool to measure the line of sight velocity of a star. Now, things in space, stars, planets, everything else, don't just move back and forth along the line of sight towards the Earth, but instead they have some component moving at right angles to that line of sight. If we look closely enough at stars over a long period of time, we can see that the nearby stars slowly move with respect to the background stars. That's known as their proper motion, and that's seeing the component of their motion at right angles to the line of sight. So if you're looking at my laser pointer and you have no way of telling whether it's moving away from or towards the camera, this motion here and this motion here will look essentially the same. You couldn't tell that in one of those cases I brought the pointer 2 or 3 inches closer to the camera than I did in the other case. You're only seeing the motion at right angles to the line between the camera and myself. You're seeing the proper motion of the laser pointer. In astronomy, if we can measure the proper motion of the star, and we can also measure its radial motion, the motion along the line of sight, we know both components of the motion, and we can tell truly the direction the star's moving in and the velocity the star's moving. So we can measure the motion of the star through our galaxy, both in terms of the component towards and away from us and the component at right angles to that. So all you need to do is add the two together to get the true motion of the star. And that allows us to build up a model of what we call the kinematics of the stars in the local area. That sounds very complicated and very confusing, but all it's saying is we can find out the way that all of the stars near the Sun are moving around the centre of the galaxy. So that's how we work out how stars move through our galaxy. But we can now, due to the incredible precision with which we can make these measurements, also apply the Doppler technique to find planets around distant stars. And that's what we're doing here at University of New South Wales in the astrophysics department. There's a very big group of people here who work searching for planets around other stars. And we do that using what we call the radial velocity method. And it's an application of the Doppler effect. So, if you have a star, and that star has a planet moving around it, that planet is far, far smaller than the star. It's not luminous, so it's too faint to see. The analogy here would be like saying, imagine you're looking at an incredibly bright lighthouse or a spotlight away in the distance. If there was a moth flying around that lighthouse, the likelihood of you being able to see it would be vanishingly small. It would just be lost in the glare from the lighthouse. And so what that means from the point of view of planets is, except for incredibly rare occasions, we cannot discover planets by seeing them directly. We have to use an indirect method where we observe the star, see that the star is doing something unusual, and infer from that that there is the presence of a planet. And there are a number of different techniques that people have chosen to use that are very useful in different situations. The one we use here at UNSW, and the one that ties in with the Doppler effect and the spectrum of stars, is the radial velocity method. If you have a star and a planet, if the planet's orbiting the star, in actuality what's happening is that both objects are moving around their common centre of gravity, the centre of mass of the system. So what that means is that because the planet's much less massive than the star, the planet will prescribe a very wide circle, its orbit, while the star wobbles backwards and forwards, left and right, very slightly. In the time it takes the planet to go once around the star will complete one full wobble in a circle and back to its origin point. This is exactly the same thing you see if you ever watch the hammer event in the athletics. So you'll see here an animation of a Scotsman throwing the hammer. As a hammer, which is our planet in this case, as a hammer swings around in a large circle, the Scotsman also orbits the centre of mass of the hammer-Scotsman system, and so you can see him wobbling backwards and forwards very slightly. If the hammer was a planet and the Scotsman was a star, therefore, the star would slowly rock back and forth along our line of sight, would sometimes be moving a little bit more towards the Earth, sometimes moving a little bit more away from the Earth. That change in motion is only of speeds of order maybe 10 meters per second, even for planets as massive as Jupiter. And Jupiter's the biggest, baddest bully in the solar system, with 318 times the mass of the Earth. It's a behemoth. Even for a planet like Jupiter, the wobble of the star would only be around 10 meters per second, which is kind of equivalent to the speed that Usain Bolt runs 100 meters. It's not much of a wobble when the star itself is probably moving at kilometers per second with respect to the Sun, which is why for a long time these wobbles were just not detectable. But over the last 20 years, it's now become possible to detect very small wobbles in stars, and so we can use the wobble of the star and the associated rocking backwards and forwards of the star's spectral lines to detect that there's a planet there. Here is some actual data taken by one of my colleagues at the Anglo-Australian Telescope at Siding Spring Observatory. And this is data showing the discovery of one of the planets found by the Anglo-Australian Planet Search. What you're seeing on the y-axis is the radial velocity of the star backwards and forwards along the line of sight from the Earth after the bulk motion of the star has been taken away. So the average velocity is 0. And what you can see, each data point is a measurement of the star's velocity at a given time, with the error bars, which are quite large, visible on the plot. And what you can see is that the star is gradually rocking backward and forward with a period of 2.8 days. So this means that there is a planet orbiting that star once every 2.8 days. So 1 year for that planet is 2.8 Earth days. This is a very massive planet, a planet like Jupiter, orbiting very, very close to its star. Keep that image in mind. If you imagine a planet on a given orbit, so if you took the Earth orbiting the Sun and then you made an exact copy of the Sun and put Jupiter at the location of the Earth's orbit going around the Sun once per year, those two planets would both cause the star to wobble. The more massive planet, Jupiter, would cause a bigger wobble because the centre of gravity of the system would be more displaced from the centre of the star, so the star would make a bigger wobble back and forth as the planet moves around it. And that's the same as if you gave the Scotsman a heavier hammer, he'd have to wobble backwards and forwards further in order to counterbalance the motion of the hammer around him. So the more massive the planet, the bigger the wobble it will produce in the star, and the easier it will be to detect. Equally, the closer the planet is to the star, the more quickly it will complete one lap of the star. For our planet that Rob discovered using the data that I just showed you, the planet went around the star once every 2.8 days, which means the star was wobbling backwards and forwards very, very quickly, which means that its maximum velocity along the line of sight would be quite great, and therefore the spectral lines would move by a large distance. What this means is that the radial velocity technique is better at detecting more massive planets than smaller planets, and it's also better at detecting planets that are very close to their star than planets that are further away from their star. But using this technique, we not only detect planets around other stars, but we can learn about those planets. We can learn the orbital period of the planet by measuring the amount of time it takes a star to rock backwards and forwards once. The longer the orbit of the planet, the longer the star takes to rock backwards and forwards. And so the time it takes to complete one oscillation is the time it takes the planet to complete one lap in orbit around the star. So that gives us the orbital period of the planet. And if we know the mass of the star, using Kepler's law that we worked out earlier on in this topic, we can also work out the distance from the planet to the star, because the distance from the planet to the star cubed will be proportional to the orbital period of the planet squared. We talked about that earlier on in the talk. The amplitude of the wobble will tell you about the mass of the planet. If you put two planets on the same orbit and one is more massive than the other, they'll have the same wobble period, but the size of the wobble will be bigger for the planet that's more massive. And so by observing the size of the wobble of the star, we can get information about the mass of the planet. And that's exactly what we do here at the University of New South Wales, using the Anglo-Australian telescope up at the Siding Spring Observatory in Coonabarabran. And to date, the Anglo-Australian Planet Search has found more than 40 planets orbiting distant stars, and there are more that are currently being prepared for announcement. So this will be an ongoing thing, and we'll keep continuing to discover planets, and the longer we observe for, the more we'll find.